So please participate today. Make sure your cameras are on. And I'll give you a heads up. Last class period, in my zero class, my computer restarted right in the middle of class. I thought I had that problem solved. I know it's done it here a few weeks ago. It hasn't done it for 2 or 3 weeks, and it did it this morning. I'm right in the middle of a lesson, and suddenly my computer shuts down and restarts. So just a heads up, that may happen. If it happens, just hang around. But we just have one lesson to cover this week. But anyway, welcome to Veterans Day. Great day in our country. Some people get this confused with Memorial Day, which Memorial Day at the end of May is when we honor those who sacrificed their lives for our country, those who died in various military service for us. So that is May. Veterans Day today is when we honor everyone who has served in our military and is currently serving in our military. So today is Veterans Day. It's a great day to set aside, just to honor those who give years of their life in dedication to our country. So, all right, Alexander, get your camera on there, sir. But yeah, Veterans Day. I don't want Veterans Day to go unnoticed, just because it is a great day that we need to recognize that those who have served and continue to serve in our country. You probably know a veteran. Most people know somebody or have someone in their family. My father was a World War II veteran. He served our country back in World War II, and along with a few of his brothers. He had 4 brothers, and I think at least 3 of them, I believe, were in the military. At least two to 3 of them. So they served in World War II. My cousin who lives in Pea Ridge, he was on a nuclear submarine. That's interesting. He served on nuclear. He can't talk a whole lot about what they did and where they went, because most of our nuclear submarines is classified. We don't. You can look it up in Google. Can't find out where they are around the world. Most of them, they spend all their time floating around the world. I mean, they don't just stay in one area generally. And so we use them because they're hard to spot. And so we go in areas that are a little questionable around the world sometimes with our nuclear submarines. So it's pretty cool that he served in that. And he told me this is what was really neat. He said, in high school, he took calculus and all that. And he's like, what good is this? I don't understand the calculus. Do I even need to know calculus? And then he joined the Navy, and he served in a nuclear submarine and had to use calculus. He said, they taught me calculus in the Navy because you had to use that in driving these submarines, because it's underwater and can go all kinds of directions, and you needed to calculate things using calculus for trajectories and all kinds of stuff. So he learned calculus, and he said it made so much more sense when I knew why I was learning it, because I was going to be in the submarine and we need to know this or this trajectory or this, for firing weapons, for driving and all that stuff. So he said, yeah, once I figured out that I really could use calculus and needed to know calculus, then it was a lot easier to learn, because he kind of, in his mind, it changed in his mind. Yes, I need to know calculus. And so suddenly it all clicked. But I thought that's interesting. We talk about when we're ever going to use calculus. Well, you might use it if you go in the Navy. You end up in a nuclear submarine. So I know we have several nuclear submarines out there. I don't even know which one he served on. I don't think he's ever told me the name of the submarine he's on. But anyway, if you see a veteran today, remember to thank them. Thank them for their service. Thank them for the fact that we have our country today and the freedoms we have today, thanks to veterans. So yes, thank your veterans today. And if you have family members that are veterans, tell them thanks for me. So, all right, let's take a look at our algebra this week, see where we're at. Get this up on the screen. Go to our grade screen as usual. If we scroll down, you should have everything turned in through Module 3. We took the test last week So everything should be done. If you got anything missing, it'll show here in Buzz. But go check to make sure that you're in good shape, and you should be ready for Module 4. So today, what's due this week? 4.01 exponential functions. So get your pencil and paper out. Get ready to start some new notes for a new unit. Remember, you can use your notes on all the tests and quizzes and assignments and even the final, which is coming up very shortly. This unit, as you can see, will get us through the rest of this semester. We will spend the next few weeks looking at exponential and logarithmic functions, which we don't spend as much time on in math. We need to spend a little more time with that. But we're going to look at exponential functions in depth today. So starting that out, let's go to our lesson 4.01. Starting out, I'm going to switch over here to our notes, our starting notes here. And this isn't really part of our notes. This is a question. So put this in the chat, or you can, raise your hand, turn on your microphone. I have two equations here, f of x and g of x. And here's what I want to know. I'm talking about exponential equations today. So which one of these is an exponential equation? Is it f of x, g of x, or both? Because if we're going to work with exponential equations, I think it's important to know what an exponential equation is, right? So what do you think? Put that in the chat. Daniel says both. Come on, folks. You finished with your breakfast. You're awake. Take a guess. This isn't for a grade, so I see a lot of boths. Both. Mary thinks both. All right, a lot of folks think okay, these are both exponential equations. All right, let's clarify that. Both of these equations have exponents. That does not mean they are exponential equations. In math, an exponential equation means that the variable, the x or the y or whatever your variable, the variable is the exponent. There is a difference between having an exponent and being an exponential equation. So what we're studying this week then is going to be f of x. This is an exponential equation. This just has an exponent. This is x to the third, the exponent is 3. This one is an exponential equation. So that is the key part to recognize exponential equations, is that the variable will be the exponent. Exponential. All right. So with that, let's get back to our lesson then. But that is an important thing to know. Have you ever watched a ball thrown high in the air? When it reaches its highest point, it seems to just float there for a second. If you haven't seen that, try it. Take a ball, throw it up in the air. There's one point there where it just seems to just freeze, right? At the top of the ball's flight, it's reached a point with 0 vertical velocity. That's when it stops and begins to fall back to the earth. On the ball's fall back down, it starts to go faster and faster each second. The velocity is changing exponentially. So we're talking about exponential equations. It doesn't have the same speed. In fact, going up, it slows down, and then starts getting faster when it comes back down. So here's what we're going to learn in this lesson. We'll be able to answer these questions. How is an exponential function created? How can the properties of exponents help solve exponential equations? So we're going to have notes on exponential properties because they're going to be very critical in solving. And what are some real world applications for exponential functions? So let's get into that. Exponential functions. So this talks about what I just had on paper. F of x equals 3 to the x is an exponential function, but g of x equals x to the third is not. And the answer they give, x to the third does have an exponent, but would not be classified as an exponential function because the variable is in the base. So to be an exponential function, the variable must be in the exponent. So let's look at some numbers. This has example here, but we're going to do this on paper in our notes. I have a table here. And we've made lots of tables over the years. You're doing this in Algebra 1 even a long time ago. So when x is 1, f of x is 2. When x is 2, f of x is 4. When x is 3, f of x is 8. When x is 4, f of x is 16. And we used tables back in Algebra 1 when we were just looking at linear equations, right? to check to see if it's linear, how much does this go up each time? Goes up 1. All right, every time the x goes up 1. So tell me what you see on the right side, f of x. You put that in the chat, you raise your hand. How much is this going up each time? What do you notice? What do you see about that? Is it consistent? Times 2? Okay, so you do see some consistency. When we look at like exponential, if this was a linear equation, if this was linear, right, where when we graph it, it's just a straight line, then when this went up 1, we would expect this to go up the same amount each time. Like this one goes up plus 2, but this one goes up plus 4, and this goes up plus 8. This is not linear because it would be like plus 2, plus 2, plus 2, or plus 5, plus, whatever it'd be consistent. This does times 2. Yeah, 4 to 8 is times 2. And you guys are right on top of that. Times 2. So what that tells us is this is base 2. So f of x must be 2 to the x power. This is an exponential equation. This table illustrates what an exponential equation was. So let's check that. It's like, okay, Mr. Brock, you're saying that's an exponential equation. Can we verify that? I mean, I see the times 2. That makes sense. Yep, it's going up times 2 every time. But does that mean it really is 2 to the x power? Well, we can check. Let's start when x equals 1. So if f of 1 equals 2, substitute 1 in for the x, what is 2 to the first power? Well, 2 to the first power is just 2. Well, let's see. 2, 2. Yep, that's what it equals when x equals 1. Okay, well, let's try 2 then. When x equals 2, if we believe this is the equation, that would mean this is 2 squared. 2 squared is 4. Yep, it is 4. How about when f is 3? 2 to the third, 2 times 2 times 2. 2 times 2 is 4 times another 2. Yep, that does equal 8. And this says 8. Huh, I think this is working out every time. And we could continue past 4, but I think 4 is certainly enough to verify. 2 times 2 times 2 times 2. So it's just, again, twice more. Okay, this is f of x equals 2 to the x power. So we verified that by substituting all of those x's into the function, and we see that. Our lesson goes through that. If you're taking notes and didn't keep up with what I was doing, it says, here's the same table. Check the increments of the x column. Should go up by 1, and it does. And then it says, look at the right side. The y's, the f of x, they go up 2, 4, 8. If we looked at it differently, they do up times 2, times 2, times 2. So it says that means this must be 2 to the x power. Check your data. That's what we did. We substituted all of the x's, and we did get the values that are in the f of x column, or the y column. There's a second example here. We won't go through both of them. You have this one available in your notes, but this one starts out with 2, 3, and 4. Skipped 1. That's not a big deal. But it has 16, 64, and 256. And when you look at how that goes up, 48 and 192, but it's times 4 each time. So this is 4 to the x power because it checks out just like we did with our function. This one checks out as 4 to the x power. So that's the basics of how an exponential function really operates, how we get the numbers, how we can form it if we're using this table and checking to see what is the exponential equation. What is the exponential function? But let's talk about, this is what I really like, solving exponential equations, solving them. Because a lot of people look at this and think, oh my gosh, how am I going to solve something where the exponent is the variable? Well, let's break it down to its most basic, simple exponential equation. If I said 3 to the x equals 3 to the 5th power, could you solve that? Could you solve that for x? Could you tell me what x equals in this case? It's like, well, I don't know, Mr. Brock. What is 3 to the 5th power? Do you need to know that? If you want to know that, we can certainly pull our calculator out and say 3 to the 5th power. 3 times 3 times 3 times 3 times 3. That's 5 threes. It's 243 if that helps you. But does it help us? So 3 to the x equals 243. That makes it harder, right? So what is x in this? Put that in the chat. What do you think x is going to be? You're like, Mr. Brock, that looks like a trick question. Is that a trick question? Anyone have a guess? What do you think x is? Paisley's going to put an answer out there. And Mary. Galen. Yeah. Don't make this hard. The only thing that's going to equal 3 to the 5th is 3 to the 5th. Right? X has to be 5. If x was 4, then you're saying 3 to the 4th equals 3 to the 5th. Right? No, that doesn't work. The only thing that equals 3 to the 5th is 3 to the 5th. It is that simple. It is that simple. Now, it's not going to look that simple as we get into this, but this is the basic concept you got to think about. If we have the same base, that's the key. If we have the same base, all we have to do is set these equal to each other. X equals 5. I just took this and set it equal to this. Because if we're raising 3 to a power, we have to raise it to the same power for it to be equal. So what you're going to see, and let's get just one step more complicated here. What if I have 2 to the x equals 8? Like, oh, Mr. Brock, that's not the same base. No, it's not. But could we write this in the same base? Could we change that? 2 to the x equals 2 to some power. Is 8 a power of 2? Yeah, we calculated up here when we was doing this table. 2 times 2 times 2 is 8. So that must be 2 to the 3rd power. So this must equal 2 to the 3rd power. Then this gets real easy. Oh, well, yeah, look, x equals 3. I just set those equal to each other because I have the same base. Yeah, that's what we have to do. When we have a problem like this, we have to figure out, can we get the same base? Because if I can get the same base, wow, this gets so easy. I just set this equal to this and get an x. And of course, we're going to get even more complicated than just a number. But this is the concept I want you to keep in mind. When we're solving an exponential equation, it's all about getting the same base. Getting the same base. That's going to be very, very key in solving exponentials. So this uses the same thing. 3 of x equals 3 to the 5th. So obviously, this is kind of what I think is the duh statement of this week. What does x equal? Well, it's obviously 3 to the 5th because that's what equals 3 to the 5th. Duh, right? Yes, it is that simple. So here they use 3 to the x equals 243. Well, if it started out this way, if you recognize that 243 is a power of 3, you rewrite it as 3 to the x equals 3 to the 5th. And then you've got this problem. It's just, oh, that's a 5. X equals 5. Easily determine that x equals 5 if we can get them written in the same base. Some exponential equations will have binomials in the exponent. That's not going to be any more tricky if we can get them in the same base. If this was 2 to the x minus 1 equals 16, now you're like, okay, now you're getting crazy, Mr. Brock. That looks really, really complicated. Well, is it? 2 to the x minus 1. What is 16 is as base 2? Is it? It is a base 2, right? It's 2 to the 4th. And you think, okay, well, that looks more complicated. Still, if you go back to this basic concept, what I say we do here, just set the exponents equal to each other because they have the same base. So we can take this and set it equal to this. Since these are the same base, that means x minus 1 must equal 4. X minus 1 must equal 4. So x must be 5. It's not that much more complicated. This is an Algebra 1 equation. X minus 1 equals 4, right? You were doing that 8th, 9th grade before. Don't let this get you where you're thinking this is real hard. This is real complicated. It's real confusing. If we get into the same base, the exponents have to be equal. That's how it works. Questions on that? Have I confused anybody with this? Because I'm trying to bring this down to the most basic level before we look at a little bit more detailed problems. All right. You can use the emojis if you got a question. Give me a thumbs up if it makes sense so far. Give me a thumbs up if it makes sense so far. I know I caught you off guard there. Yep. Use your little emojis there. Or thumbs down if someone's confused. All right. So let me know if you're confused. All right. No thumbs down. Say I did a thumbs down. All right. We're feeling good. We're feeling good about this. So good. Because all right. Because this can be this simple. This is the concept I want you to keep in mind. I just need to be the same base, and then the exponents would be set equal to each other. All right. We are going to be working a lot with properties of exponents. And so we need to go and review these. I know you had these in Algebra 2. We've looked at these, but let's go back over these properties because they're going to be very key in solving exponential equations. So we're going to put this in our notes. They've got them here in Buzz if you want to look at them on here, but we're going to write them in our notes because sometimes we can do examples that make more sense than that. Is that like what? Okay, so I got to turn the paper over. Product property. So put this in your notes because you're going to use these a lot. The product property we're going to use a considerable amount and some other ones. So the product property said if we have x raised to the power of m, just a variable, times x raised to the power of n, another variable. The product, remember you multiply two things, you get a product? That means we can just take x and add those exponents together. So an example, if we have x to the third times x to the fourth, that's the same thing as the x to the 3 plus 4 or x to the 7th. So it's always good if you can, when you write down a property, write down an example. So I know how this works because we can get lost with the variables. If I have x to the third times x to the fourth, I could just multiply those together. I mean, add those together when I'm multiplying these and get 7. And how do we know that works? Well, x times x times x is x to the third. And if I'm multiplying that times x to the fourth, I'm multiplying it times 4x's. Well, that's just x to the 7th because I have x multiplied by itself 7 times. So that's x to the third times x to the fourth. And I can just add those together. Okay, let's look at the quotient property. Quotient property. What is quotient? We get the quotient when we divide something, right? So if we have x to the m power and we're dividing it by x to the n power, our quotient property says we can take x to the m minus n. So if we have x to the fifth being divided by x to the third, that's the same thing as x 5 minus 3 or x squared. Like, well, how does that work, Mr. Brock? Well, think about it. If we have x to the fifth, we have x times x times x times x, and we're dividing that by x to the third, we can simplify. X divided by x is just 1. So that's just 1. X divided by x, that's 1. That's 1. What's left? We have x squared. Well, you can say over 1 if you want to. That's all that's left on the bottom is a 1. But that's just x squared. So that is the quotient property. The power property, we're going to use this one a lot with solving exponential equations. All right, if I'm going too fast, remember you do have these in the lesson right here, quotient property, all of that. It's just that I'm giving a little bit different explanation. This is b to the 5/6 divided by b to the 1/4, and so they're using fractions. I'm trying to simplify it because it's the same principle. I'm just using m and n or using whole numbers instead of fractions, subtracting a fraction. Power property, or the power to a power property if you want, because the power property says if I have x to the m power and I raise that to the n power, that says I can take x and multiply m times n. I just multiply the exponents when I have a power to a power. So let's have an example of that. If I have x squared and I'm raising that to the third power, this property says I can take 2 times 3, and that's the same thing as x to the 6th power. Okay, let's work this one out. X squared, that's x times x. And I'm taking that to the third power, which means I'm multiplying this times itself 3 times. So x times x times x times x, there's 2 times, but I'm doing it another time, x times x. Well, that's x times x times x times x times x times x. I'm multiplying x times itself 6 times. So yeah, I see how the power property works. That makes a lot of sense. Mathematically, we can see that and how that works. The other property is the negative exponents, and it's a little bit more confusing. Oh, I like how they did that. That's pretty good. Negative exponents kind of has 2 different ways. If we have x, let's do negative. Write it down. If we have a negative exponent, it's important that our final answer has no negative exponents. If we have x to the negative m power, right, we're being raised to a negative power. Our final answer shouldn't have a negative power. We can make that positive by moving it to a denominator. 1 over x to the m is the same as x to the negative m. And likewise, if we have 1 over x to the negative m, we can move that to the numerator and make it positive, which means it really be over 1. But if it's over 1, we never write, every number is over 1. So let's see, and I like the example they gave. If we have 3 over x to the negative 5th, that is the same thing. The 3 is just a number. It's not being taken to a negative exponent. It's 3 to the 1st. So it stays up as in the numerator, but this can move up, and that would be the same thing as 3x to the positive fifth. Or let's do another example. If I have, I'm going to put 2y to the negative third power over 3x to the negative 2 power. Like I've got negative exponents everywhere. That would be the same as 2. This would move down, but this would move up. The 2 and the 3 stay where they're at. X would move up here to become positive. The y would need to move down in the denominator to become positive. So this is the same thing as this. But when we're simplifying things, we don't want to have negative exponents. We need to make them positive. And the way we do that is in this method right here. So these are the 4 things you want in your notes: the product property, the quotient property, the power property, and the negative exponent property. This is what we're going to be using as we're solving exponential equations, is going back to these basic properties of exponents. And again, you do have these right here in Buzz, if that was quicker than you wanted to cover that. But in the interest of time, all right, they have a video we can watch on the first one here. And this is examples of rewriting an exponential equation with equal bases. Remember I said that's the big key. The key is to get the bases the same number. And this gets a little trickier, but I want to look at this, and then we'll break it down after we see how they do this. But let's take a look at their video explaining this first, and then we'll dig into that.
First, create equal bases. Before solving for the variable, the bases of each exponential expression in the equation must be identical. Rewrite the numbers 256 and 16 with a base of 4 and exponents 4 and 2, respectively. According to the properties of exponents, when the denominator of a fraction contains an exponent, such as 1 over 4 to the 4th power, you can rewrite the expression with a negative exponent. On the right side of the equal sign, there is a power raised to a power. By the power of a power property, these exponents will be multiplied. Be sure to distribute. Now, solve for the variable. Once the bases are identical, eliminate both bases and find the value of the variable. Now, check your work. Substitute the value of the variable into the original equation to confirm the solution. The solution x equals 7 is correct.
That was a good example, because looking at this problem right off the bat, you might be thinking, wow, there's no way I can make those the same. Yeah, they did a good job of doing that. Now I want to look at something on that, because a lot of times in math, there's more than one way to solve things, right? Because the way they solved it was not the way I would have solved it right off the bat when I look at it. The important thing is we've got to get these to be the same base, right? So they changed this to base 4. So they said, okay, this is 4 squared, and it's being raised to the power of x minus 9, which put us to that power of a power thing. And then over here they said, oh, this is base 4 as well, and so they said that's 4 times 4, which is 16, times 4 times 4. So that's to the 4th power, and they went 4 to the 4th power. So these aren't the same base yet, because this is in the denominator. So to make it base 4, they had to change it to a negative exponent so that they would have base 4 on both sides. But there's more than one way to do this. 256 and 16. Did I write this as base 16? Is that possible? Do you recognize that? If you don't have your multiplication tables down at the 16s, I understand. But if we're looking for a common base, 256 is 16 squared. 16 squared, 16 times 16 is 256. There's nothing wrong with doing 1 over 16 squared equals 16 to the x minus 9, which means I can rewrite this as 16 to the negative 2 power equals 16 to the x minus 9 power. I've got the same base. It doesn't matter if it's a 6 or a 4, as long as it's the same. If it's the same base, I can now set this equal to this. Negative 2 equals x minus 9. I add 9. That's the same answer they got. They just went farther down in bases. It's like, why did they choose 4? They could have chosen base 2. This is 2 to a power and 2 to a power. We could have brought all this way down to be 1 over 2 to the 256 is, what is that, 8th power or something? And, 2 to the 4th to the x minus 9. I mean, you can change it to any basis. There's more than one option there, because that 256 and 16 could be base 16, base 4, base 2. The key, and I'll repeat this time and again, is these just have to be the same. If those are the same, now it's just a simple algebra 1 problem. Set this equal to that and solve. As long as these are the same. So like I say, don't overcomplicate it. You're just trying to get the same base. And sometimes, yeah, that may take a little work, because you might not recognize right off the bat. You might want to get the calculator out and start figuring out what base do these have in common. What numbers? Let's look at example 2. Oh, this is the good one. We're going to write this one down, because now we're getting into square roots. It's like, oh, now we got to pay attention to stuff that I have forgotten about. And this is raised to the power of 12x. I'm writing this down so we can work this in our notes. All right. Yeah, I've written this problem down. Square root of 11 to the power of 12x equals 121 to the x plus 1. All right. Look at that, and somebody give me an idea. Where should I even start? Let's look at that for a moment. What base do you think we might have a chance to use on both sides? All right, Alexander's got a shot at it. All right, good job, Kaylee. So if we look at it, and we're trying to figure out a number to square on both sides, this is already a square root of 11. 121 is, if we remember our multiplication tables, 11 squared is 121. So this is 11 squared. Do you know, do you remember? It's been a while since we've done that. That was Algebra 2. Can we write this as an exponent? This is a radical. If you remember how to convert radicals to exponents, the square root of 11 is the same thing as 11 raised to the 1/2 power. Remember how that works? If you have a number under here, like 2, and it's being raised to the 3rd power, and this is, let's say that's the 4th power, to convert that to a rational exponent, you keep the same base, The 3 goes on top of the fraction. Whatever's outside here goes on bottom of the fraction. If you remember that, this stays as the top. This moves to the bottom. Well, that's the same thing here. This, since there's no number, that's an assumed 2. So that's what would go on bottom of the fraction. This is just 11, so that's 11 to the first power. So the square root of 11 is 11 to the 1/2 power. So we can rewrite this as 11 to the 1/2 power, and it's being taken to the power of 12x. Over here, we said 121 is 11 squared, so we can rewrite that as 11 squared, and it's being taken to the power of x plus 1. All right, I'll put that in parentheses, just remember that. We've got the same base. We have base 11 on both sides, but we've got to pull out our exponents that we just made notes on. And I said we're going to use this power to a power property pretty frequently. If we have a power taken to a power, we multiply those together. We have a power taken to a power on both sides. So this is 11 to the 1/2 times 12x. We multiply those together, equals 11 to the 2 times x plus 1. Both sides are the same. They're both a power to a power. We're getting there. 11. What is 1/2 times 12x? Put that in the chat. What is a 1/2 times 12x? A little refresher. We're dealing with a fraction there. Almost, Alexander. I'm gonna. There you go. Daniel's got it. Yeah, it is 6. 1/2 times 12. But don't forget, this is 6x. I put that equals a little too close over there. This is 11 to the. That is 6x. 1/2 times 12x, 6x. Over here, we got to remember to distribute. Got to multiply the 2 times both terms. So this is actually 2x plus 2. If I see common mistakes that's easy to make, you might put 2x plus 1 if you're just not paying attention. That's why I put that in parentheses. Keep that in parentheses just to remember I'm distributing the 2 to both terms. Yay, we've gotten exactly where we want to be. These are the same base, which means just get rid of the bases and set this equal to each other. 6x equals 2x plus 2. Finally, we're down to an algebra 1 problem. What's x equal? I'm going to wait. Work that on your notes or in your head if you want to. Tell me what x equals before I finish it here on paper. You're thinking, is this really that simple, Mr. Brock? Yes, this is an algebra 1 problem now. I'll give you the first step. We need the x's on the same side. You're still struggling with that. What do you got? There you go. X equals 2/4, which of course we know to simplify, x equals 1/2. Now we need to check that. We're like, oh my gosh, checking that? Yep, we're going to try this. Square root of 11 raised to the power of 12 times 1/2. Twelve times 1/2 equals 121 to the power of 1/2 plus 1. So 1.5. So like, oh, Mr. Brock, this is getting hard just to check it. Oh, we got this. So let's do this first. The square root of a, let's rewrite this. That's 11 to the 1/2 power. 12 times a half is 6 to the 6th power. Let's go ahead and make this 11, because if we're checking it, if we get the same base, we can get this. This is 1.5, right? A half plus 1 is 1.5. So we can say 3/2 or 1.5, however you like to do that. Power to a power means we multiply those. This is 11 to the 3rd power. What's 2 times 3/2? 2 times 3/2. This is 2 over 1. So 2 times 3 is 6. 1 times 2 is 2. 6 over 2. We're good. 11 thirds equals 11 thirds. When we checked our answer of 1/2, that is exactly correct. So even something that looks as nasty as this starting out, if we can just get it to the same base, it gets real easy. We just have to get it to the same base. And sometimes that can take a little bit of work. But here is the work here. Create equal bases where they convert the square root of 11 to 11 to the 1/2 power to the power of 12x. Same thing over here. They take 121, 11 squared, where we end up with 6x equals 11 to the 2x plus 2 power. You can drop the bases, set the exponents equal to each other. X equals 1/2. And then they substitute it back in. And they went ahead and just made it a number, 11 to the 3rd power, which is 1331. But if I got 11 to the 3rd equals 11 to the 3rd, that's the same. But they actually calculated it out. So the solution is correct. All right, very good. Let's look over here. Applications. So let's talk about it. Oh, this is a good one. Suppose you were to find a bottle with a genie inside who's going to grant you one of 2 wishes. Here, I'm gonna take this off here. One of 2 wishes. You can. Here's your choice. So put this in your chat. I want to see what you want. The genie says, all right, for the next 30 days, I will give you $100 a day. That's option A. Option A. I'll give you $100 every day for the next 30 days. And you're like, yes. He says, or I'll give you a penny today. And then tomorrow I'll come back and I'll give you 2 pennies. And then I'll give you 3 pennies in the third. And I'll do this for 30 days. Every day I'll just give you twice what I gave you before. So I'll give you 4 pennies in the 3rd day. Mix that through. I'll give you 4. I'll double the day 2. And then I'll give you 8 pennies. So, by the end of the week, you'll have a lot of pennies. What do you want? Do you want option B with the penny? You want option A with $100? Like after 15 days, you'll have $1,500 or a whole bunch of pennies. Everybody wants some pennies. All right. Everybody locked in? Everybody wants to change their mind? Everybody wants pennies? Let's look at it. We have a chart here. $100 every day. We know what that's going to get. You're going to have $3,000, right? You'll have $3,000 at the end of the month. But if we took the penny, look, after 10 days, we get $5 that day. At 15 days, we'd have $160. On day 30, 5,368,709, which means for the whole month, for 30 days, you'd end up with over $10 million because it's growing exponentially. Exponentially. See, it doesn't seem much for the first, for the first 14 days, you're getting less money than you would have on option A. See, I'm still getting $81 from day 14. We're up on the other option. I got $100 that day. I only got 81, but it starts catching up in a hurry. On day 15, hey, instead of $100, I'm getting 163. Now I'm starting to get better, and it makes up for it real quick because now by day 18, you're over $1,000 for that one day. Exponential growth. So an exponential growth function is a function where the initial amount grows significantly as time passes. Like doubling the amount of money in your pocket every day for 30 days is an exponential growth function. And it can be represented by this: a penny that doubles by day. The t is by day. And if we graph that, we can actually graph this. We'll just change it to an x since our graph works on x's, not t's. So take this off to the x power. Take out the dollar sign too. Y equals. So there we go. Let's change this to just days, 1 day at a time. Okay, so day 1, what do we got? We got a penny, right? Day 2, oh, 4 cents. Well, day 0 is when you get the penny. That's what they consider really the first day on here. Day 0, first day. That's when they give you a penny, and it's going to double and double and double till pretty soon. Man, see, by 30 days, it's so steep, it's going up so fast. You got to zoom out a long ways. Boy, it's getting really, when it doubles. Day 17, I'm at 1,300, and it's almost straight up. I can't even scroll up high enough to get to the top of that on day 30 because it starts going up so very, very fast. Where the other graph of the other was just $100 a day. Y equals 100x. Now, well, it goes up. Up here, it'll cross real quick. So what are they the same? They're the same right here between day 17 and 18. But the one is just an exponential line, and it won't be nearly the same. $100 a day. $10 million. Oh, here, they graphed it as well. But yeah, we just put that on the graph. Look, it goes up very, very fast. There's many applications of exponential growth. One example can be found when computing compound interest in banking. Interest is money that a financial institution like a bank contributes to your account based on the amount of money in the account. Most accounts earn simple interest, which is interest based on your principal. The principal is the amount of money you deposit. That's the amount you start with. Compound interest is interest based not only on the principal, but on the interest you already got. So if I give you interest, you got $100 and I give you interest. So now I got $102. Next time I give you interest, I'll give you interest on the $102 because you left that $2 in there with the rest of the money. So now it's getting interest. And so then you get interest on that. So the basic equation, we probably should write this down because we're going to apply this. This is our interest formula. T is the principal. Start amount. All right, that's how much you start with. That's how much you put in the bank to start with, the principal. Wait, did I spell that right? Which principal is this? Oh no, it's an AL just like the other one. All right. The principal amount, the starting amount. R is the interest rate. Should be a decimal. Which for a decimal, 5% equals 0.05. You might want that in your notes because it should be a decimal. And this is the number of times interest is received per year. Per year. That's the key there. And then T equals years. So here are the key parts. I'll leave it up there for a moment. We're writing it down. T is the years, P is the starting amount, R is the interest rate as a decimal, and N is the number of times interest is received per year. All right, let me leave that up there a moment for those of you diligently putting that in your notes, because we will have some interest problems to work. This is the real life stuff here. You need to know in your bank account or your investment account, if you know how many times you receive interest per year and you know the interest rate, you can calculate how much money you'll have after so long of a time. And it does have that information right here on page 5. A is the amount. A is the amount of money. A is the total amount that you'll end up with. Notice that 1 is being added to the fraction r over n. That represents the initial principal. If you didn't have the 1 plus, it would just tell you the amount of interest you received. It wouldn't tell you the amount of money in the bank. So let's see. If $100 is invested at 5% per year, compounded quarterly, that's what tells you how many times a year you get interest. Quarterly. A quarter is 1/4, right? So 4 times a year, this account's giving you interest. And wants to know how much it will be worth at the end of 2 years. So let's watch them work one of these. And we'll go from there.
If $100 is invested at an interest rate of 5% per year, compounded quarterly, how much will the investment be worth at the end of 2 years? To answer this question, first use the scenario to define each variable. The principal, P, is $100. The interest rate on the account is 5%, which is written as the decimal 5/100ths. The account is compounded quarterly, which means 4 times each year. Therefore, n is 4. The question asks you to find the account value after 2 years. So, t equals 2. Now that only one variable is left, use the order of operations to solve for that variable. When working with money, round the solution to the nearest cent, or nearest hundredths. So, after 2 years at a 5% interest rate, compounded quarterly, the initial $100 investment will be worth about $110.45.
Okay, so what we see there is if you just get 5% on your $100, that means every year you make $5, right? 5% of 100 is $5, which means after 2 years you'd have $110. But the 45 cents shows that you're leaving that interest, you're getting interest on the interest. So after that first year, you're not getting interest on $100, you're getting interest on $105 because you'd have like over $105 after the first year. You'd actually have more than that because you're getting it every 3 months. You're getting it 4 times a year. So after the first 3 months, you'd get $1.25, right? You get 1/4 of that year's interest. But then you're getting interest on $101.25 in the next 3 months. So you're getting a little more than $1.25 that time, and it just goes up each time as your interest is accrued each quarter. So as the account is compounded more and more frequently, if it's monthly, it'll be a little bigger than that even. It'll just keep going up just a little bit the more often that you get interest. Monthly, weekly, daily, hourly. Yeah, well, I wish I could get hourly interest. The amount in the account will not change as significantly, and eventually it might change at all as it gets more and more. But when the principal, the frequency increases, the amount earned increases. So look, here's the same calculations. If we would have got monthly instead of quarterly. So quarterly, we ended up with what? 110.45. If we got every month, we'd have 110.49. So we'd end up with 4 more cents. If we got interest every week, we'd have 110.51. If we got it every day, 52. So it doesn't make a huge amount, but it does add a little bit. But we're only talking about $100 invested. Imagine if you invested $100,000 somewhere, then these numbers would start meaning more. But the more often it is compounded, the better off you are. There is one other formula here. Interest on an account is compounding continuously, which means every instant of a second. There is another formula we can put on here. A equals principal ERT. This is continuous. Continuously. TERT. R is the rate, T is the time, E is a number. Like, what do you mean E is a number? I'm talking about the number E. In math, it's right here on our calculator, right here, E. E is 2.71828182845. It's a number. It's about Euler's number. Euler was the mathematician that come up with this number. It's used in mathematics. It's the number E, and that is the number E. So the principal times the number E raised to the power of the rate times the time for continuous interest. So if $500 invested in an account that has an interest rate of 6% per year, compounded continuously, every millisecond, you're getting your millisecond worth of interest. So using E, A equals PERT. So $500 invested now, 6% for 3 years, receiving continuous interest. When you run the calculations, 0.06 times 3 is 0.18. So E raised to the power of 0.18 is 1.197217363 multiplied by the 500, make almost $100. It's $598.60 now after 3 years. $598.61. That's how much it's worth at 3 years. $500 at 6%, 3 years. Here's more examples if you need more examples on exponential growth, but we want to look at some sample problems here. This is population. Population's LERT, where really the L is the initial population. It's the same as the PERT. It just uses a different variable. And it says if it grows 10% per year, 50 people lived there originally. How many people will there be 11 years later? We use the continuous growth, and there'll be 150 people. Then here's another one with bacteria. So this is where you use those continuous. Let's stop that for a moment there. The continuous interest is kind of ludicrous. You're never going to find a bank or an institution that's going to give you continuous interest. So that PERT is like, okay, that's kind of worthless. Except for there are lots of cases to use this, especially in science. When we're talking about bacteria and bacteria tripling in size every day, that's continuous. It's growing every second. It's growing more bacteria. It's not just like, oh, once a day, boom, now some more bacteria is there. Now we're waiting, boom, now there's no. It's continuous growth. It's constantly multiplying. This bacteria is continually growing. So that's when you use that type of equation. That's continuously growing, the PERT, in a bacteria situation like that. So that's where that kind of comes in there. Sometimes they give you different formulas based on the bacteria. But if you have something like that and they don't give you an equation to use, then do the beginning amount with the ERT. But just depends on what they give you. All right, let's go to page 6. Exponential decay. All right, that's the other case we have, is sometimes things aren't growing, they're shrinking, right? Like if you have actual food laying out, it'll decay and it'll weigh less, it'll slowly go away. So let's look at an exponential decay function. The base of an exponential decay must be between 0 and 1. So 15,000. Okay, let's write something down on this. Exponential decay. The exponential decay, it says, could be the amount is the starting amount, and they use L for a starting amount. 1 minus R to the T. 1 minus the rate. Like if we know it's decaying at 10% per day, It's going away. It's evaporating or whatever's happening. If we start with 1,000 of this substance, and we know it's decaying at 10%, 10% decay. 10% decay. Our formula would be 1 minus 10% or 0.1. And we want to know after 7 days. So our time would be 7. 7 days. We start with 1,000 of whatever bacteria or whatever it's evaporating, decaying at 10%. So when we simplify that, it's 1,000 times 0.9 to the 7th. Now, if you think about it, this makes sense. If it decays 10%, that means every day we've got 90% left. If we have 0.9, we started with 100%, but instead of 1, I've got 0.9. I've got 90%. So let's do the calculations and see what that would mean after 7 days. Bringing our calculator back up. So 0.9 to the 7th power times 1,000. We have 478 point, I guess we'll round it to 2 digits. See, it's a little different than if we'd have said, well, we're losing 10% every day. So after 7 days, I've lost 70%. No, it doesn't work that way. I would only have 300. Because if I'm losing 10% per day, the first day I've got 1,000. The second day I've got 900 because I've lost 10%. But now I'm only losing 10% of the 900. So I lost 90. I've got 810 left. See, now I'm only losing 81 that day. So every day it's not losing 100 because that's only the first day. Each day it's losing 90% of what's left. 90% of what's left. So we're losing 81. We're losing 90. Losing 100. So it changes every day. That's why we end up with 478.30 after 7 days, not 300, because we didn't lose 100 a day. So this is like an exponential decay, where growth would be, may give you that this lab sample doubles every day. Could be something like that. This doubles every day. And wants to know after how many days, would it double? So generally, they'll usually give you a formula that they want you to use for decay or for growth. Let's see here. Oh, this is a good thing about decay. The value of your car, that's going down. So let's see. Let me write this formula down. The amount that your car is worth would be 1 minus R D, and it's going to start at $15,000. How much does it say it's going to decay? Oh, we want to know 5 years. And 20%. Okay, so using our formula here, if you have a car, it's worth $15,000. It's probably depreciating 20% per year. That's not uncommon. If it's newer, it may depreciate faster at the beginning, but we're going to say on average, you lose 20% of value of your car. So the amount after 5 years will be, this is L again, the starting amount of $15,000. It's losing 20%, so it's 1 minus 0.20 for 5 years. So it's 15,000 times 1 minus 20. You got 80% value left every year. So let's see what the amount after 5 years is. How much is that car worth 5 years later when you paid $15,000 for it? Okay, 0.8 to the 5th power. 0.8 raised to the 5th power times $15,000. Your car's worth about $4,900. That's probably pretty accurate. Cars go down in value pretty fast. It's hard to pay them off faster than they appreciate. 49, 15, 20. That's what they got. 49, 15, 20. So there's a graph looking at it. Seeing that value going down. Lesson summary. How's an exponential function created? Properties of exponents, real world applications. So this gives you steps. Create equal bases, solve for the variable, check your work. Here's a compound interest formula, continuous interest formula. So we have those in our notes. And then exponential growth, exponential decay. The biggest thing to know in exponential growth and exponential decay is the number that's being multiplied by. Whatever multiplied, the rate taken to the time, your starting principle. If this R is greater than 1, it's growth. Right? Because the number's getting bigger. If it's R is less than 1, it's decay. Like here, we've only got 80%. See, it's going down. Every year we got 80% of what we start with. If this is 1.1, that means it'd be growing. 1 point would be 10% higher every year. So whatever number's in that parentheses, if it's greater than 1, if you end up with a number bigger than 1, it's going to grow. If it's less than 1, it's going to, like this is doubling every year. It's 2. See, it's going to get twice as much every year. But this is only 0.9. It's going to go down every year. Growth and decay. What number's being raised to an exponent there? That will tell you whether it's a growth or decay formula. And that's what it talks about right here. The base of the exponent must be greater than 1 or between 0 and 1 if it's getting smaller. Solve each of the following exponential problems. 10 raised to the 2a plus 3 equals 10a minus 4. Solve that for a. Nice. Just throw an answer out there, see if I get it right. Incorrect. Incorrect. Okay, that'll tell me how many. 6 to the b minus 7 equals 36. So I'll just choose an answer. Correct. 125c equals 25c minus 4. He's got to get those to the same base and then solve the exponents. Here's an exponential growth problem. $75 invested, 8% per year, compounded monthly. What's it worth in 15 years? 15 years. And there's more of those. But activity 3, exponential decay depreciates at 20%. So work those. So let's look at our assignment for the week. What exponential function represents this data? Is this 5 to the x? Is it x to the 5th? Is it 4x plus 9? X to the 4th plus 9? Solve this. 3x raised to the power of x minus 5 equals 9. Same base. Get to the same base. 64x and 16x. Get those to the same base. 1/25 equals 5x to the 4th. Get those to the same base. Oh, we have 10 problems this week. Okay. There we go. Oh, here we got some invested at 4% per year, 6% per year. Here's a bacteria that triples. R is 3, triples. Sailboat depreciates at 15% of its original value each year. It was $9,500. How much it's worth after 7 years? 100 milligrams of medicine leaves your bloodstream at 14% per hour. How much is left in your system after 10 hours? Use this formula, LERT. It tells you which formula to use to figure that out. All right. You guys have any trouble with this? This is an 8A Friday, so we only have class on Thursday. So thank you for your participation today. I'm sure I'll hear wonderful things from our principal when she tells me how class went, because she sat in for at least the first half of class today. And then she went on to do other things. But yeah, just the one lesson this week. We'll start looking at, let's see, logarithmic functions next week. Yay, logarithmic functions. So we'll get a good taste of those. But this unit will take us the rest of the semester. We'll finish this up right before finals week. And if you got any questions or problems, you can come to class Thursday or email me. Otherwise, I'll give you the last 15 minutes to maybe get this week's assignment done before you get to advisory time. But, all right, guys, the rest of the time is yours. Enjoy. We'll see you next time.